More than 2,000 years ago, on a stretch of Mediterranean coastline, Roman engineers poured a mixture of volcanic ash, lime, and seawater into wooden molds and created something that modern science is still struggling to fully replicate. That structure still stands today, battered by waves, salt, and time, while much of the concrete poured by 20th century engineers has already crumbled into ruin. Somewhere in the deserts of Egypt, blocks weighing as much as a loaded jumbo jet were lifted, moved and stacked with a precision that some modern architects admit they could not casually reproduce without cranes, lasers, and computer modeling. And high in the Andes, without a single iron tool, without the wheel, without a written language as we understand it, another civilization built cities that have survived earthquakes capable of leveling modern concrete apartment blocks. This is not a coincidence. This is not luck. Across continents, across centuries, across cultures that never made contact with one another, ancient builders arrived at solutions so effective, so durable, and so precisely calculated that today's engineers are not inventing new answers. They are rediscovering old ones. The visual, sweeping drone footage over ancient ruins, slowly transitioning between Roman aqueducts, Egyptian pyramids, and Incan stone walls. For most of the 20th century, the story we told ourselves about ancient technology was simple and slightly condescending. We assumed that older meant cruder. We assumed that without modern machinery, ancient builders relied mostly on brute force, unlimited slave labor, and trial and error. But as archaeology has matured, as material scientists have begun testing ancient structures at the molecular level, and as structural engineers have modeled ancient buildings using the same software used for skyscrapers, a very different picture has emerged. Ancient civilizations were not stumbling toward solutions. In many cases, they were working from a genuinely sophisticated understanding of material science, structural mechanics, hydraulics, and even chemistry, knowledge that was later lost, forgotten, or simply not written down in a form we could easily interpret. Today, we call this rediscovery, but in truth, we are often just catching up. Visual, split-screen comparison of a modern engineering blueprint and an ancient stone diagram or hieroglyph depicting construction. To understand why this matters, we need to travel back to the ancient world, not as tourists admiring old stones, but as engineers trying to solve the same problems our ancestors solved, moving impossible weights, building structures that could outlast empires, and creating materials that could withstand forces we still struggle to predict. Let's begin with concrete, because it is perhaps the clearest example of ancient knowledge outperforming modern practice. Roman concrete, known as opus caementitium, was used to build structures like the Pantheon in Rome, whose unreinforced concrete dome remains, to this day, the largest of its kind on Earth. It was also used to build harbors, breakwaters, and piers that were submerged directly in seawater, an environment that destroys modern concrete within decades. Yet many of these structures are still intact after 2,000 years of relentless wave action. Visual, underwater archaeological footage of Roman harbor ruins, waves crashing against ancient concrete piers. For decades, engineers assumed Roman concrete was simply less advanced than modern Portland cement, just lucky enough to survive. But research conducted by geologists and material scientists, including detailed mineralogical studies of samples taken from Roman harbor structures, revealed something remarkable. When seawater seeped into microscopic cracks in Roman concrete, it triggered a chemical reaction with volcanic minerals in the mixture, and instead of eroding the material, the seawater actually grew new crystalline structures inside those cracks. In other words, Roman concrete didn't just resist damage from the sea, it used the sea to heal itself. Modern concrete, by contrast, is engineered to be strong on day one, but gradually weakens as water and salt corrode the steel reinforcement bars inside it. Roman concrete had no steel reinforcement at all, and needed none, because Roman engineers were not fighting against natural chemical processes, they were designing with them. This wasn't accidental. Roman writers, like Vitruvius, documented detailed instructions for selecting specific volcanic ash from specific regions, understanding that not all volcanic material produced the same reaction. This was applied materials science, refined through empirical testing over generations, long before anyone had a word for chemistry as we know it. Visual, close-up microscopic imaging or CGI animation showing crystal formation inside ancient concrete. Today, engineering teams around the world, including researchers funded by organizations studying long-term infrastructure durability, are actively trying to reverse engineer Roman concrete formulas, hoping to create modern materials that could last centuries instead of decades. This is not nostalgia, it's a practical response to a very real problem. Much of the concrete infrastructure built in the last 100 years is already failing, while structures the Romans built are still standing. If Roman concrete demonstrates ancient chemical intelligence, the pyramids of Egypt demonstrate something equally staggering: Ancient logistical and structural intelligence on an almost unimaginable scale. Visual, golden hour aerial shot of the Giza Plateau, pyramids catching the last light of day. The Great Pyramid of Giza was built more than 4,500 years ago, using over 2 million limestone and granite blocks, some weighing as much as 80 tons. For centuries, popular imagination pictured armies of enslaved workers dragging these blocks across the desert by brute force alone. But archaeological excavations at nearby worker villages have completely transformed our understanding. Researchers uncovered bakeries capable of feeding thousands of workers daily, medical facilities showing evidence of healed bone fractures, meaning injured workers were cared for, not discarded, and organized worker districts suggesting a skilled, paid labor force rather than a slave population. Visual, excavation site showing ancient bakery ovens, tools, and worker housing foundations. This wasn't just brute labor, it was a coordinated national project involving supply chains, food logistics, medical care, skilled stonemasons, surveyors, and administrators. Essentially, ancient project management on the scale of a modern mega infrastructure project. Engineers today studying the pyramid's construction have proposed models involving massive ramps, sledges lubricated with water poured onto sand, a technique confirmed by ancient Egyptian tomb paintings showing workers pouring liquid in front of a sledge to reduce friction, later validated by physics experiments showing that wetting sand can reduce dragging resistance by as much as 50%. Visual, CGI reconstruction of workers pouring water in front of a sledge hauling a massive stone block. Even more astonishing is the pyramid's precision. The Great Pyramid's base is leveled within just a couple of centimeters across a footprint covering over 5 hectares, and its 4 sides align with true north with an accuracy that rivals modern surveying instruments. Some researchers believe ancient Egyptian architects may have used astronomical observations, tracking the rising and setting points of stars, to calculate true north with remarkable accuracy, essentially transforming the night sky into a surveying tool. This raises an uncomfortable question for modern engineers. How did a civilization without iron tools, without the wheel for heavy transport, and without any known lifting machinery achieve tolerances that would challenge construction crews equipped with laser levels and hydraulic cranes today? The honest answer is that we still don't have a complete explanation. We have compelling theories, strong archaeological evidence for organized labor and clever mechanical techniques, but the full picture of how granite blocks weighing dozens of tons were lifted to precise positions high above the desert floor remains, in some respects, an open engineering puzzle. Now travel forward roughly 3,000 years and thousands of kilometers away to the mountains of Peru, where the Inca civilization built Machu Picchu without a written language, without iron tools, and without the wheel, yet created a city that has survived some of the most powerful earthquakes on Earth almost completely intact. The secret lies in a construction technique called ashlar masonry, in which massive stone blocks were cut and shaped so precisely that they fit together without any mortar at all, so precisely that in many walls you cannot slide even a thin blade between the stones. This wasn't simply aesthetic perfectionism, it was earthquake engineering, refined through generations of trial, observation, and adaptation in one of the most seismically active regions on the planet. Modern structural engineers, using seismic simulation technology, have studied these walls and confirmed what Incan builders apparently understood empirically centuries ago. The tightly interlocked stones can move slightly during an earthquake, shifting a few millimeters and then settling back into place, rather than cracking under sudden stress the way rigid, mortared structures often do. In essence, Incan walls were designed to flex and dance during seismic events, absorbing energy instead of resisting it rigidly. The same principle, allowing structures to flex rather than rigidly resist force, is now a foundational concept in modern seismic engineering, used in everything from Japanese skyscrapers to California bridges, where engineers install flexible joints and dampers to let buildings sway safely during earthquakes instead of standing rigid until they shatter. The Inca were applying this principle with stone, by hand, without any of our modern vocabulary for physics, 500 years before seismologists formalized the concept. Machu Picchu's engineering brilliance doesn't end with its walls. The city sits atop a network of hidden drainage channels, carefully sloped foundations, and permeable stone layers that prevent the mountainside from becoming waterlogged and collapsing during the region's intense rainy seasons. Excavations have revealed an underground drainage system so effective that, centuries after the city's abandonment, it still channels rainwater safely away from the buildings today. This is not a coincidence of good luck. This is deliberate hydrological engineering, built into the very foundation of the city, invisible to the average visitor, but essential to the site's survival for over 5 centuries. If Machu Picchu shows sophisticated seismic and hydraulic engineering, the site of Baalbek in modern-day Lebanon presents perhaps the single greatest unanswered question in ancient construction. Within the Roman era temple complex, there sits a stone block known as the Stone of the Pregnant Woman, weighing an estimated 1,000 tons. Nearby lies another, even larger unfinished megalith, estimated at close to 1,600 tons, heavier than several fully loaded Boeing 747 aircraft combined. Visual, dramatic, ground-level shot showing the sheer scale of the Baalbek megaliths with a human figure for size reference. To this day, no confirmed method has been definitively proven for how these stones were quarried, transported, and, in the case of similarly massive blocks already incorporated into the temple platform, lifted and precisely positioned. Some researchers propose massive wooden sledges, teams of hundreds of workers, and complex systems of ropes and levers. Engineering analysis suggests such methods are theoretically possible, but would have required an extraordinary, almost unprecedented coordination of manpower and mechanical ingenuity, even by Roman standards, which were themselves remarkably advanced. What makes Baalbek particularly fascinating is that it demonstrates something crucial about ancient engineering that's easy to forget. Even the Romans, one of history's most technologically capable civilizations, seem to have been operating at the very outer edge of what their tools and manpower could achieve. These weren't gods or lost super-civilizations. They were extraordinarily determined, extraordinarily organized humans, pushing the boundaries of physics and logistics using ropes, timber, bronze tools, and an almost incomprehensible amount of patience. Long before Rome, long before Egypt's pyramids, another site forces us to reconsider everything we thought we knew about when sophisticated engineering began. Gobekli Tepe, in modern-day Turkey, dates back roughly 11,600 years, predating Stonehenge by around 6,000 years, and predating the invention of writing, pottery, and even agriculture itself. Yet at Gobekli Tepe, hunter-gatherer communities, people we once assumed were too primitive to organize large-scale construction, carved and erected T-shaped limestone pillars weighing up to 10 tons, arranged in precise circular formations, decorated with detailed carvings of animals and abstract symbols. This discovery, still being fully excavated and studied, fundamentally overturned the long-standing assumption that large-scale monumental architecture required organized agricultural societies first. Instead, Gobekli Tepe suggests that the desire to build something monumental, something communal and symbolically powerful, may have been one of the very forces that pushed early humans towards settled, organized society in the first place, rather than the other way around. In other words, ancient engineering may not be a byproduct of civilization. It may be one of the reasons civilization began at all. Traveling south to the deserts of modern-day Jordan, another ancient achievement forces us to reconsider assumptions about hydraulic engineering. The city of Petra, carved directly into rose-colored sandstone cliffs by the Nabatean civilization over 2,000 years ago, thrived in one of the most arid environments on Earth, yet supported a population, along with visiting caravans, numbering in the tens of thousands. The secret lay not in the carved facades tourists photograph today, but in what lies hidden beneath the desert floor, an extraordinarily sophisticated water management system, including hundreds of cisterns, dams, and ceramic pipes engineered with precise gradients to control water flow using gravity alone, capturing and storing seasonal flash floods that would otherwise be lost within hours. Archaeological surveys have mapped kilometers of these channels, revealing an ancient civilization that had, in effect, engineered an artificial oasis in the middle of the desert. Modern hydraulic engineers studying arid region water management have noted that Nabatean techniques, capturing flash floodwater quickly, filtering sediment through multi-stage basins, and distributing water via gravity-fed channels rather than energy-intensive pumps, remain relevant today, particularly for regions facing water scarcity. Some contemporary sustainable engineering projects in desert climates have explicitly drawn inspiration from ancient Nabatean methods, essentially rediscovering solutions that were quietly waiting in the sandstone for 2,000 years. Beneath the landscape of central Turkey lies yet another engineering marvel, one that remained largely hidden until relatively recently. The underground cities of Cappadocia, carved into soft volcanic rock, descend as deep as 18 stories below the surface, complete with ventilation shafts, stables, wine presses, chapels, and enormous rolling stone doors designed to seal off sections of the city during times of danger. These cities, some capable of sheltering thousands of people along with their livestock for extended periods, feature ventilation systems so effective that fresh air continues to circulate through some shafts even today, without any mechanical assistance. Engineers studying these structures have noted the sophisticated understanding of airflow, structural load distribution through soft rock, and defensive architecture. Multiple independent cities interconnected by tunnels, engineered so that a single breach wouldn't compromise the entire underground network. So a visual cutaway CGI diagram showing the multi-level layout of an underground Cappadocian city. Once again, we find ourselves facing the same pattern. A civilization without modern tools, without powered machinery, achieving levels of engineering sophistication and ventilation, structural stability, and urban planning that would challenge architects even today. So what connects all of these achievements? Roman self-healing concrete, Egypt's impossibly precise pyramids, Incan earthquake-resistant walls, Baalbek's incomprehensible megaliths, Gobekli Tepe's civilization-defining monuments, Petra's desert water mastery,